Hi, my name's DiChello, and this summer I worked with Dr. Jackson on matrix-based analysis of climate feedbacks. So first, a feedback is a process where some of the output is returned to an input. And there's two types, positive and negative. A positive feedback is one that amplifies the response. So think of a microphone and speaker system. When the speaker is too loud, the microphone picks up some of the sound waves. So that causes the process to amplify the response, and the speaker kind of goes haywire. A negative feedback would be one that dampens the response. So for example, think of a coffee cup. If your coffee's cold and you microwave it, when you take it out, it's going to emit a lot of heat and try to reach an equilibrium. When we're looking at the global sense, we're taking the global average change in temperature. So our input is going to be an energy forcing that I'm going to call epsilon, and the units is watts per meter squared. The output is a change in temperature, and there's two types of change in temperature we're interested in. The base case, which is delta T 0, and that's when we run the change in temperature when we run the system without the feedback active. There's also a change in temperature called the delta T alpha, which is the alpha case, and that's when we run the system with the feedback active. We're interested in the sensitivity of the system, which is the change in output per forcing. So in our case, it's the change in temperature per unit forcing. And the sensitivity is important to climate scientists because climate scientists are interested in the change in temperature when there's a doubling of CO2 in our environment, which would be a forcing of 4 watts per meter squared. And we'd be able to find the change in temperature by multiplying the sensitivity of our climate system by 4. The gain is the comparison of the system run with the feedback active versus not active. So there's a couple types of feedback systems in our environment, and one important one that I'm going to be talking a lot about today is ice albedo feedback. Ice albedo feedback is just the reflection of the sun's energy back into space. As the Earth warms, though, ice and snow melt, so there's less surface area covered by ice and snow to be able to reflect the sun's light into the sun's energy back into space. So it's a positive feedback. Water vapor is also a positive feedback because as the Earth warms, more water evaporates, so we have more water vapor in our atmosphere. The more water vapor in our atmosphere causes the water vapor to actually trap the heat because it's a greenhouse gas, so it's also a positive feedback. Clouds is currently not classified as positive or negative feedback in our environment. It's being researched to this day because it has tendencies of both, and scientists aren't sure where it balances out. It acts as a positive feedback in certain ways because, again, clouds are made of water vapor, so it traps heat. But it also acts as a negative feedback because the more clouds there are, the sun's energy is actually reflected off the clouds like ice albedo. So it acts in both ways, and it's unsure how it balances out. Planck feedback is a negative feedback in our system, and it keeps our climate system under control because, like the coffee cup, as the Earth warms, we're going to emit more heat, and that really keeps our system under control. So I studied the environment in a more nuanced way by separating the Earth into 48 latitudinal boxes. In doing so, that caused the forcing to now be an epsilon, and where each box has one entry in the vector, and the output perturbation, delta T, is also a vector. So I'm going to be talking a lot about the tropics and extratropics in this for my research. So just to be clear, the tropics is 0 degrees to 30 degrees in the north and in the south, and the extratropics regions are 30 degrees to 90 degrees in the north and the south as well. For my simulation, I used the Globally Resolved Energy Balance Model, or the GREB model, and this was created by Dommagett and Fultner. So we had these these scalar model equations before, and now since we have vectors being forced and a vector output, we have to adjust the equation so we could use vectors and matrices. You see here that there's the base case, that we have the system output here as vectors, but we simulated that. So we were able to use these two equations to solve for our new sensitivity matrices, lambda 0 and lambda alpha. Once we had those, we're able to find the gain matrix. And the gain matrix, again, is that comparison between the system with the feedback active and not active. Since we're using a matrix model, we're able to use this partial differential equation down here to find the specific, the local and non-local effects of a forcing between the two, between various regions. So from now on, we're only going to be talking about the northern hemisphere because that's what I looked at specifically. When I force in the tropics region, the extratropics down here, you see there's a lot of cooling going on. And then when I forced in the extratropics, we see that the tropics had a lot of warming going on. To study why this is happening, I took zonal averages. Again, separating into our four main areas, the two tropics areas and the two extratropic areas, where one up here, this is the South Pole, and down here is the North Pole. We have, in this one, the forcing along the diagonal, we subtracted the forcing to be able to focus specifically on the non-local responses. So we're going to look at that the same northern hemisphere section where the forcing was in the northern tropics and in the northern extratropics. When the forcing was in the northern tropics, there was an increase, or when there was an increase in temperature in the northern tropics base case, there was a decrease in temperature in the extratropics with ice albedo active. So this caused actually a cooling, and as you can see on the scale over here, it's actually, this blue indicates that it's negative. When the extratropics had a heat increase for the base case, the tropics had an increase in temperature with the ice albedo active. So, and as you can see, this is the highest increase in temperature non-locally. To be able to study why this is the case, we found a specific forcing to implement where the average change in temperature would be 0 everywhere except for in the third box, or in the northern tropics. And so this red line is the average change in temperature in the zones, and the blue line is the actual change in temperature for the whole, for all 48 boxes. As you can see here, the gradient is increased. The increase in gradient actually is what caused this negative change in temperature in the northern extratropics, although the average change in temperature, remember, was 0. So, so to be able to study, so having this allows us to be able to figure out what exactly ice albedo's response is to this forcing. So I took the average change in ice albedo in the last 5 years of simulation, and over here you see from 30 north to 90 north, this is the extratropics region where we are interested in studying the non-local effect. And remember, the change in temperature was 0 here, the average change in temperature. So over here we see the ice coverage increase a lot. And that's where the ice line is, and where the ice line is where it's going. The ice will increase or melt more than the poles because it's not surrounded by ice. And this increase happened with 0 change in temperature. So that's the effect ice albedo had on the system. You also see in the shaded plot where the warmer colors are an increase in ice albedo and the cooler colors are a decrease in albedo. Over here we see that there's an increase across almost the whole extratropics in ice albedo. So ice albedo is increasing, which in turn would cause a cooling in the northern extratropics. In conclusion, the non-local effect of a heat forcing in the northern tropics would cause an increase in ice albedo in the northern extratropics. The next step in this would be to investigate the southern hemisphere and see how it acts in comparison. and also to do the same simulation and process for water vapor feedback. Any questions? Yeah.
If you go back to this slide, why are there two or a few blue dots?
So that's actually showing that there's a decrease in ice albedo there, and that's over the land, and that's due to a separate phenomenon that's separate than this that I don't have knowledge of yet.
Okay.
Yeah.
Okay, so I'm trying to understand this like intuitively. So you're saying if you have heat forcing in the tropics, it pulls the extratropics down due to increased ice albedo. Is that because there's more evaporation and then you get more ice deposition, so that then you start getting the positive feedback of increasing ice means more cooling, means increasing ice means more cooling, and so forth?
Can you say your question again?
So I'm wondering, like, why would adding heat to the tropics cool down the extratropics, if I'm understanding you correctly?
Okay.
And my guess is if you add heat to the tropics, you get more evaporation there, and then if that gets deposited in the extratropics, you can then have a feedback loop of ice buildup.
So that's because this temperature gradient here, this decrease here, or like this, the slope of this is increased. So it's so mathematically that's why, but
Right, and I'm trying to figure out physically
I
why
believe
is
in
that
the climate, and correct me if I'm wrong, it has to do with the way the atmospheric heat transport works. There's a lot of correlation between the atmospheric heat transport and how the ice albedo is affected. Mm-hmm.
Is there any reason to think that to do this simulation again in the southern hemisphere would have a different result than doing it in the northern hemisphere?
Yeah, so in the southern hemisphere, because Antarctica is surrounded by the ocean, there's actually less of a polar amplification. So there should be, so typically there's less warming there. I don't know what that means for ice albedo. I guess it would mean that there'd be more of an increase in ice albedo, I would guess. But there should be some differences in the southern hemisphere.
I'm sorry.
So it looks like you had a PDE that you discretized for this model?
Well, the model was created for us, the GRED model.
Was that continuous in space? It looked like the model you put up, I thought looked like it was continuous in space.
It's globally resolved, so it's separated by 96 different longitude in 48 latitudes.
Okay, so it was discrete in space. Is there any reason to believe that you'd have any different effect from different choice of, say, binning in this?
There probably would be a little bit of a difference, but this is the most resolved model that we had access to.
So there's an increase in ice albedo?
Yeah, so there's an increase in the amount of ice coverage. So we're actually having a little bit of an ice line, like the ice line is growing.
I thought the big thing was that the ice caps are melting.
So this is specifically for when I forced in the extratropic region, so when I put energy in there. Currently, right now, the ice, we are in a global warming state.
Okay, so this isn't like current stuff?
This is just specifically to understand how ice albedo is affected with various heat forcings.
Okay.
Yes.
You mentioned earlier what happened. You also tried forcing heat in the extratropics. What effect did that have on the tropics again?
In the extratropics here, when I forced in the extratropics, there was the most non-local warming in the tropics. So that would probably be due to when you force in the extratropics, you're forcing directly where the ice is. So there's more melting, which causes more evaporation. And then that's when atmospheric heat transport, so the transportation of the heat and water vapor kicks in.
Any other questions? All right, let's thank Kristen again.